Hello students, good morning. Today's lecture we are going to see about the NMR logging, Introduction to Nuclear Magnetic Resonance Logging. So basic introduction on NMR logging. So let's go to the presentation. So introduction to nuclear magnetic resonance. So today's presentation, so we are going to see about the introduction to nuclear magnetic resonance. So overview of NMR, what are the principles of NMR and petrophysics, what are the logging tools, etc. So this NMR provides a complete processing of nuclear magnetic resonance data using the geolog softwares. But the theory, principles, and application of NMR logging technology, and this is information is designed for the geolog users who are going to analyze and interpret the NMR data. So to use this NMR application, you should be familiar with the following functions in the geologs: data loading, editing, viewing data using the well explored application and project management, etc. So we'll see in separate lecture about the NMR geolog application software, but let us go to the this petrophysics introduction of this NMR. So to assess the NMR application, so you have to do the petrophysics NMR with the help of geolog well application. So you have to do the functions geolog and the module launchers and also working tables. So this is the starting application of geolog well applications in NMR, that is petrophysics. Then this is next. So what is the principles of NMR? So NMR is an acronym for nuclear magnetic resonance. So NMR relies on simple principles that the molecular behavior of materials can be affected by a magnetic field. So in order to understand the role of the NMR, which plays an important role in the so it is important to understand the basic principles and measurements. So this introduction of NMR provided as follows. What are the principles, petrophysics, logging tools, and the inversions or the mathematical models. So next slide. So what is NMR? So NMR relates to the dynamics of nuclear spin magnetic moments in the presence of a magnetic field. That is influence of magnetic field. So you can see the diagram, the influence of magnetic field. So NMR is that is the ability that will affect the nucleus of this strong magnetic field and determine the properties from the interaction with application of magnetic field. Application of magnetic field. So the model is providing the behavior to consider the nuclei as bar magnets. So it is possible to align certain nuclei with magnetic properties in magnetic field. Therefore, the nuclear bar magnets have two important properties: the magnetic moment, which determines the strength of the interaction, and the spin. In the magnetic field, we have the nuclear spin, which causes the nuclear bar magnet to proceed around the applied magnetic field. So this nuclear spin process at a frequency that is dependent on the strength of the magnetic field. Therefore, the nuclear spin possesses some resonance frequencies which is related to the strength of the magnetic field. Therefore, this will termed as nuclear magnetic resonance. Then this NMR is relevant to the formation evaluation specialist in oil and gas engineering because the behavior of nuclear spin is related to the properties of the fluids, most importantly, the chemical composition of the fluids and the viscosity of the fluids. And where the fluid is contained in the porous medium, the interaction of the nuclear spins with the pore surface perturbs the behavior of the nuclear spins. So this is your basics. What is NMR? So next slide. So NMR uses three magnetic fields. NMR measurements. You can see the three magnetic fields, that is static B0, then oscillatory RF pulses PI, then local magnetic field fluctuations, unpaired electrons and neighboring nuclei. There is some involvement of some basic physics also here. So you can see the diagram BI versus B0 with RF. So NMR uses three magnetic fields. So what are they? So the NMR measurement used in petrophysical analysis of the rocks in three different magnetic fields. You can see in the diagram the static magnetic field, that is B0, and magnetic field generated using the oscillatory frequency pulses BI. This field is applied at normal to the static field, that is B0. Then the local magnetic field fluctuations, which are generated by unpaired electrons and neighboring nucleus. You can see here neighboring nucleus. Then this is your next slide, that is isolation of hydrogen nuclei. So in the applied magnetic field, the proton that possesses with an angular frequency called the Larmor frequency F0 determined by the strength of the magnetic field B0 and the gyromagnetic ratio G. So by tuning the RF radio frequency of the NMR instrument to the Larmor frequency, the signal from hydrogen can be maximized. That is isolation of hydrogen nuclei. Then bigger applied fields, you can use these equations. So n by n equal to e to the power of minus e by kt, where e is the energy difference between the spin states and k is the Boltzmann constant, temperature of the Kelvin, that is T. So this is the alignments of both parallel and anti-parallel magnetic fields in the diagram. It will be shown in the next slide. So what we are using here? So the number of spins in the lower energy that level and that is n plus, and the slightly outnumbers the number in the upper level, that is n minus. So lower level and upper level. So n minus and n plus. And this is your Boltzmann statistics, which determines the net magnetization will be very small and few protons with the lower energy state. So you have to understand here the lower and upper level energy states, which that is the prediction of Boltzmann statistics. Then you can see here the classical physics. So no magnetic field in the first diagram, then apply proton process B0 with F0, then protons align parallel and anti-parallel in B0. And number fourth diagram, you can see the net magnetization is by Boltzmann constant, which we discussed in the above equation. So detectable magnetization very small compared to B0. So this is the alignment of proton spins in the magnetic field, that is by explained in this classical physics. This four diagram, so you can go through it. Then detection of nuclei using the spin tipping. So what is spin tipping? The process of spin tipping can be described in force process, that is RF pulse applied at 90 degrees to B0. Then when the RF pulse is turned off, the proton spins are detectable in the transverse plane. And number 3, additionally, when the RF radio frequency pulse is switched off, or that is turned off, the proton begins to return to B0 and the signal decays. So after certain time t, the signal is completely decayed. That is detection of nuclei using spin tipping. So this is the concept of spin tipping. The next slide. So you can see the next one, spin tipping using the RF pulse applied at 90 degrees to the V field, magnetic field. So you can see the concept of spin tipping. RF pulse applied at 90 degrees to V0 tips spins into the transverse plane and signal is detectable in the X-ray, XY transverse plane. Then number 3, when the RF pulse is turned off, protons return to the P0, the signal decays. And number 4, you can see after time t, spins are aligned in the plane P0, the plane, there is no signal. This is the 4. So this is the spin tipping using the radio frequency pulse applied to 90 degree at the magnetic field B0. So this is your T0, Ti versus T2 relaxation spin tipping. So what is the Ti relaxation? Relates to the time taken, how much time taken for the proton to spins and translate from the random alignment to becoming the aligned to the direction of the magnetic field B0. So the difference between the T1 and T2 can be considered as a measurement of relaxation to B0 in the two different measurement directions. Then, so Ti as TL refers to the XYZ plane and T2 refers to the XY plane. So you have to understand this. And then next one, so you can see the spin tipping using RF pulse applied at 90 degrees. This spin tipping. So next, so this is the relaxation expressed in terms of B0 exposure time. That is T1 relaxation time, nuclear polarization, the exposure time. 1 minus e to the power of minus t by T1. So this is the relaxation T1 expressed in terms of B0. So the time constant describes how much mz returns to its equilibrium called the spin lattice relaxation time. And the equation governing this behavior function is of the time initial displacement, that is mz equal to m0 multiplied by 1 minus e to the power of minus t by t1. T1 is therefore defined as the time required to change the z component of the magnetization by factor of E. So this is the T1 relaxation expressed in terms of B0. Then this is the spin dephasing in the T2 XY plane. Now we are going to dephasing in T2. So the RF we can see after 90-degree pulse, the spins process in unison and net magnetization is preserved. Then dephasing of the spin results in a reduction of the net magnetization. So this is a spin dephasing in the T2 plane. So after the 90 degrees, the B1 pulse has been applied. The proton spins are aligned to the direction BI. You can see the diagram on the left, at which time the detected signal is at maximum. So after a short time, the proton spins to the dephasing causes the proton to spread out in the T2 plane, that is in the diagram on the right, because the spins are no longer aligned in the same. So that is called spin dephasing XY plane. So now refocusing the spin echoes using the CPMG sequence. So you can see the refocusing 90-degree pulse focuses the spins in transfer planes. And then second one, due to FID, spins dephase until net magnetization. Number 3, at 180 degrees RF radio frequency pulse reverse the precession of the spin, refocusing the signal. Number 4, after a short time, the spin, we can see here, after the spins are refocused, creating a spin echo. So that is your third. You can see the last diagram, refocusing of the proton spins. refocusing of the proton spins. So now the CPMG pulse sequence you can see here. So FID receiver, TE spin echo, so 90, 180 and 180 transmitter. You can see here that CPMG pulse sequence. Then irreversible dephasing, T2 described by the CPMG echo train. So you can see here irreversible dephasing T2 determined by the equation mt equal to m0 e minus e to the power minus t by t2. So first echo, third echo, then time t. So this is the irreversible dephasing. So in the petrophysics, NMR data imparts important informations about porosity, pore size, bound water, fluid types and permeability. So we are understanding the process that contribute the NMR relaxation provides the model for extracting the petrophysical parameters from this NMR data. So in the porosity means in the fluid filled rocks, the volume of rock occupied with the fluid is equal to porosity. Therefore, petrophysical NMR measurements utilizing the hydrogen proton spins to generate the signal because the hydrogen is abundant in fluids. So the magnitude of the NMR signal is proportional to the formation of fluid volume. So when the proton signals are aligned in the magnetic field, then NMR signal is proportional to the porosity of the rock. Therefore, the start of the CPNG experiment. So at the t equal to 0, before the relaxation of the proton, the spins has occurred. The signal is proportional to porosity. So the NMR logging tools are calibrated using the 100% porosity reference. So this is your polarization and weight timings. That is time taken to align the hydrogen protons in magnetic field depends on the T1 relaxation time. Then this experiment consists of two parts, the polarization followed by the CPMG pulse sequence. So the wait time is that is allowed for the exposure to the B0 field before the commencement of the spin tipping using the BA1 or radio frequency pulse. So now NMR relaxation process T2 decays in two ways. One is the surface relaxation, then bulk fluid relaxation, then molecular diffusion. So all these processes act in parallel and therefore the TT of the T2 of the pore fluid is given by 1 by T2 equal to 1 by T2 bulk plus 1 by T2 surface plus 1 by T2 diffusion. So transverse relaxation T2, T2 by bulk relaxation of the fluid, then due to surface relaxation T surface and T diffusion. So this is the surface relaxation in porous media is due to the interaction of the proton spins in the fluid with the pore surface. So the proton spins are subject to the random motion which is called as Brownian motions. So the relaxation, simple process we understood. So this is your surface relaxation. So you can see here rock grain spin diffuse to pore wall where a proton spin has probability for being relaxed. So you can see here the surface relaxation, T2 relaxation related to the pore size by the following equation. So this is your equation where S by V equal to surface volume to ratio of the pore and rho 2 is this T2 surface equal to T2 surface relaxivity. So that is relation between the pore size S by V is the only valid in the fast diffusion limit. Then bulk fluid relaxation. Every fluid has an intrinsic relaxation that is determined by the properties of fluid including the viscosity and chemical composition. So diffusion, that is your relaxation is due to the diffusion caused by molecular diffusion in the presence of gradient field during the CPMG experiment. Then echo spacing. The effects of diffusion relaxation can be negated by using the short inter-echo spacing, time between CPMG pulses and TE. So after comparing the multiple CPG experiments, variable interspacing, the diffusion or coefficient can be exploited and used to identify fluids. So this is your multi-exponential decay. You can see here multi-exponential decay. Then NMR, this modeling process referred to the inversion. So now we will conduct concept of inversion. So NMR and petrophysics. So you can see here rock bulk volume, total porosity, then minerals, rock matrix, clay bound water, capillary bound water, free water and hydrocarbons. So that is your effective porosity. So this understanding T2 distributions is shown in the following diagram. Then this is your rules for bulk relaxation. 100% water saturated pores, then oil in water wet pores, which are shown in this diagram. Rules for bulk relaxation. The non-wetting fluid relaxation with bulk properties. So these are the assumptions. Clay bound water is often used. And permeability. There are two permeability models in NMR logging. So SDR model, then Timur Coates model. So what are the wettability issues? In porous rocks, it's normally assumed that non-wetting phase will display bulk relaxation properties. So this is your NMR properties of the reservoir fluids. You can see here fluid viscosity, time, T1, T2, relaxation time, hydrogen index, diffusion coefficients, then NMR properties, differential spectrums, delta, weight time experiments, DTW. Then this is your hydrocarbon NMR tools. Hydrocarbon using polarization contrast. So you can see the time domain, identify hydrocarbon by exploiting the polarization contrast between fluids, diffusion analysis. So this is your diffusion analysis, the NMR tools. You can see the water shift, shifted water and water, the diffusion analysis. Equation. So the application of capillary pressure. So from theoretical point, the T2 distribution provides the distribution of pore size and relates to the pore size distribution of the rocks. So 1 by T2 equal to rho into S by V, pore. So where T2 is the relaxation, S by V is the surface to volume ratio and gamma is the coefficient. And this is the diameter formula. The averaging pseudo capillary pressure curves over specific reservoir intervals allows the opportunity to construct the J function and saturation height functions. So this is a CMR tool, numerical CMR tool. You can see here sensitive region, pad types, antenna, etc. And this is the polarization velocity correction. And this is your NMR tool, NUMERS MRIL tool, dual frequency bandwidth. Then hydrocarbon typing, CTP logging, that is sequential frequency using frequency cycling, provides the better resolutions. Then hydrocarbon typings, switching the frequency allows the multiple experiment to be made with a single logging run. Then this is C by TP logging. You can see here MRL CTP mode. Something on inversion. Now the principle of data for the interpretation NMR wireline logs in the T2 distributions are explained here. That is your initial signal amplitude proportional to the number of hydrogens nuclei associated with the pore fluids. And now you can see the spin echo amplitudes. Idealized NMR measurements are done here. So at the time T0, the total signal is proportional to the number of hydrogen nuclei associated with pore fluids. Idealized NMR measure. Number 2, that is signal amplitude decays exponentially the time in a manner similar to the familiar thermal decay time measurements. So this is the idealized NMR measurement. And this is your T2 cutoff for all the T2 distribution interpreted in terms of pore size and fluid distribution. Then this is your NMR signal resulting from 3 signal exponential decays. You can see here the inversion. So what are the inversion problems? The following inversion problems in the echo has been noted. So the echo train related to the T distribution by the following relation. That is called CPMG relaxation curve. This is the product of 3 single exponential decays B. So you can see clearly in the diagram. So equation 14 describes the forward problems. Then this is a regularization equation by this equation. Then L2 solution, L1 and L2 hybrid solutions. And single value decomposition, SVD solution by this equation. Then simultaneous inversions. All the inversion methods can be used to process NMR data consist of 3 main, that is more than one set of relaxation data. So this is the summary MRAL CITP mode summary diagram using the equation of CTP data. So this is your CPMG echo train from the short burst frequency T2, which are averaged and then inverted separately from the long CPMG echo train. So we successfully completed today the introduction to NMR logging. So today's presentation we have completed basic of introduction to the NMR logging. So this is a new topic in our channel. So we will have more on NMR logging, the geolog software, where we can analyze very clearly about the petrophysical properties. Thank you. Subscribe my channel.